Another way that we can find the roots of a function is by using the Newton-Raphson method. This is given to us in the formula book. It works by drawing a tangent at a point on the function. So we pick a point, we draw a tangent, and the tangent intersects the x-axis closer to the root, and then we draw another tangent at that point with that new x value. And then we get closer again, we draw another tangent with a new x value, and we get closer and closer to the root as we go. This does not work. So you need to know that it does not work if you try and draw the tangent at a turning point, because at a turning point, there's no gradient. The gradient 0, it doesn't intersect the x-axis, so it can't work. So let's have a look at a question. F of x is x squared minus 3x minus 6. Show that the equation f of x equals 0 has a root in the interval, so between 4 and 5. If there is a root between 4 and 5, we should see a change of sign. So we're going to do f of 4 and f of 5, and we should see a change of sign. So f of 4 is 4 squared minus 3 fours minus 6, which is negative 2. And if we substitute 5 into the equation, we get 4. We get positive. So we have a change of sign and a continuous function. Therefore, we have a root in the interval 4 to 5. Using x0 as 5 as a first approximation, apply the Newton-Raphson method once to obtain a second approximation for alpha. So this is where we're going to use the Newton-Raphson. So x0 is 5. x0 is 5. F of 5, we know, we've already worked it out, is 4. And f prime of 5, that means differentiate it and substitute in 5. So we're going to have to differentiate. Times by the power, take 1 off the power. So the gradient function is 2x minus 3. So if we put 5 into the gradient function, 2 5s, 10, take away 3, is 7. So our x0 is 5, f of 5 is 4, and f prime 5, f dash 5, is 7. So we can just substitute these in now. So x1, our next approximation, is x0, which is 5. Take away f of 5, which is 4, over f prime 5, which is 7. So it's 5 take away 4 sevenths. And that's 31 sevenths, or 4.43. Okay, one for you to try. See if you can give it a go. So firstly, show that the equation f of x equals 0 has a root in the interval 0 to 1. So we're going to do f of 0 and f of 1. So we've got e to the power of 0 plus 2 zeros, take away 3, which is negative 2. And for 1, we get 1.72. So again, we've got a change of sign and a continuous function. Using x0 as 1, as a first approximation, apply the Newton-Raphson method. So we know x0 is 1, f of 1 is 1.72, and I'm actually going to store that as a, and we need the gradient function. So f prime x, f dash x, the gradient function, when we differentiate e, it stays the same. 2x differentiates to give 2, and the negative 3 has got no gradient. So if we put 1 into our gradient function, we get 4.72. So now we can just substitute in to our Newton-Raphson. So we've got x1 is going to be equal to x0, which is 1. Take away f of 1, which was 1.72, over f prime f dash 1, which was 4.72. So it's 1 take away what we saved as a over our last answer, and we get 0.636. Another question, same thing. So show that the equation f of x equals 0 has a root in the interval between 0 and 1. So we're just going to do f of 0 and f of 1, change of sign, and therefore there's a root. So 2 zeros, take away cos 0 is negative 1. And 2 ones, take away cos 1 is 1.46. So again, change of sign, and f of x is continuous. Therefore, we have a root in that interval. Now we're going to use the Newton-Raphson method. So x0 is 1. We need f of 1, which is 1.46, which we're going to, again, I'm going to store that in the calculator. And we need our gradient function. So 2x differentiates to give 2. Negative cos x will differentiate to give a positive sign. So cos differentiates to give negative sign. So negative cos will give a positive sign. And so f, if we put 1 into our gradient function, we get 2 plus sine 1, which is 2.84. So the Newton-Raphson method says that x1, our next approximation, is our previous one, which was 1. Take away f of 1, which was 1.46, over 1 into our gradient function, 2.84. So 1 minus a over our last answer, 0.486. One for you to try. Give it a go. So firstly, show that the equation has a root in the interval. So we're going to do f of 2 and f of 3 and see if we get a change of sign. So we have 2 cubed minus 2 times 2 squared minus 5, which is negative 5. For 3, we get a positive 4. So again, we have the change of sign. And it's a continuous function. Therefore, we have a root in the interval 2 to 3. Now the Newton-Raphson method, our first approximation, x0, is 3. F of 3 is 4. And our gradient function is going to be 3x squared minus 4x. So if we put our 3 into our gradient function, we've got 3 times 3 squared minus 4 3's, which is 15. So now we're just substituting in. We've got our Newton-Raphson method. So we've got our next answer. Our next approximation is our first approximation, which was 3. Take away f of 3, which was 4, over 3 into our gradient function, which was 15. So 3 take away 4/15 is 2.73 recurring. Another question, this one is different because it shows that f of x has a turning point in the interval 3 to 4. So our turning point is going to be where our gradient is 0, not where it crosses the x-axis, where the gradient is 0. So we're going to need to find the gradient function. So 3x squared minus 10x plus 1. And we want to know where that equals 0. So that is our function that we're working with. So it should equal 0 in the between 3 and 4. So if we substitute in 3, substitute in 4, we should get a change of sign. So we have 3 times 3 squared minus 10 3's plus 1, which is negative 2. And for 4, we get a positive 9. So again, we have the change of sign and the continuous function. Therefore, we have a turning point in the 3 and 4. I would write that all down if I had a bit more space. Using x0 as 3 as a first approximation, use a Newton-Raphson method once to obtain a second approximation. So the function we're using this time is 3x squared minus 10x plus 1. So in our Newton-Raphson method, that is actually going to be our f of x, and we're going to have to differentiate that to get the gradient of the gradient function. So we want to know this time where the gradient function is equal to 0. So we have a first approximation as 3. I'm going to write f of x, f of 3, even though it is the gradient function. But for the purpose of our Newton-Raphson, this is the function we're working with. F of 3 is negative 2. And our gradient function is going to be our gradient of the gradient. The second differential, so 6x minus 10. And if we put 3 into that, 6 3's, take away 10, is 8. So we have our second approximation is our first approximation. Take away f of 3 over 3 into our gradient function. So it's 3 minus minus a quarter, which is 3 1/4. One for you to try. See if you can give it a go. So again, we're looking for a turning point. That's where the gradient is equal to 0, not where the function is equal to 0. So the function we're working with is actually 3x squared minus 6x minus 4. So let's see if we have a turning point in that interval. If we've got a turning point, we will get a change of sign. So we have 3 times 2 squared minus 6 2's minus 4, which is negative 4. And if we substitute 3 into our function, we get a 5. So again, change of sign, continuous function, therefore alpha in this interval. Then the Newton-Raphson method. So we're going to obtain a second approximation. The first one is 3. So x0 is 3. F of 3. So again, we're working with our gradient function. So f of 3 this time is going to be our 5. We're treating it as if this is our original function. So we need the gradient function, which is 6x take away 6. So this is our second differential, but we're treating it as if it's the gradient function. So we want to put 3 into our gradient function. 6 3's take away 6 will be 12. So our next approximation is our previous approximation. Take away f of our approximation, which is 5. F of 3 is 5. Over 3 into the gradient function, which is 12. So it's going to be 3 take away 5/12, which is 31/12 or 2.58.